Welcome to a new video about Butterworth response using LC ladder configurations. This is our example number 4. In this example we will continue with the high-pass filter design and we will work out the calculation, also the specifications, checking using the simulations in SPICE. So let's look at our example. We have the objective, as said, we need to design a Butterworth response filter. It must be passive, an LC ladder configuration of a high-pass type high-pass filter. And we need to use 50 ohm double terminated shunt input circuit. The specifications are shown here. We need the maximum passband ripple, 1 dB, minimum stop band attenuation, 20 dB, and the passband frequency must be 8 MHz and stop band frequency must be 4 MHz. And I discussed in the previous example, this is the generalized filter block. The RS and RL are the normalized source and the load resistor, and they are now 1 ohm each. And we need to scale it up later to get this 50 ohm double terminated shunt input circuit. So let's look at our solutions. First step is the calculation of the filter order N. And for the Butterworth response we need the epsilon values, the epsilon P for the passband, which is related to A max. We know A max is 1 dB, so you just substitute that in this formula, you get now 0.5088 approximately. In a similar form, epsilon S, you relate it to the A minimum. And if you now also substitute the 20 dB here, you get 9.9499 approximately. Now taking these two values together, and you substitute that in this formula for the filter order N, you get log of the epsilon S over epsilon P divided by the log of the FP over Fs. Now, if you now do the math here again, you get here 4.2894 approximately, but we need to have an integer value, so we need to round it up and give it an N as 5. So we need a 5th order filter. Well, the second step is then the calculation of the frequency scaling factor, Kf, which is also the cutoff frequency, omega f over fc, or omega c of fc. So that is what we do. The Kf now for the high-pass configuration is given by the omega p times the epsilon p to the power 1 over n, where n is the filter order, which is calculated, which is 5. Now we know that omega p is 2 pi times the FP, so it is 2 pi times the 8 million hertz or 8 megahertz. So that's why we have here 16 pi times 10 to the power 6 times our epsilon and to the power 1 over 5. Now when you now calculate this, you get now 43.91 megaradians per second, which is approximately, in this case, turning to this in hertz, 6.989 megahertz. Now step 3 is calculate your scaled component values, and we use our table Butterworth response for the LC ladder low pass filter. From there we will then go to the high pass filter. So you see we need a 5th order, that is actually this row, you can see that here. So we need these 5 values in a normalized form to go to the values for the high pass filter. And this table now here, because we just focus on these 5 values, we can create the high pass filter from this prototype low pass filter. You see the C1, L2, C3, L4 and C5. Those are X1, X2, X3, X4 and X5. So they're actually now in this order. Again, they are all normalized. So there's 1 ohm, 1 ohm, and this C1 is actually have a value of 0.618 farads, and the L2, which is now the value here, is 1.6180 henries, etc. So moving on to the transformation from the low pass to the high pass, you see the transformation is quite straightforward. The capacitors will turn in inductors, and inductors will turn into capacitors. The C1 will turn in a parallel L, and the L2 here, which is given here, will be in a series CS1. So let's see what the formulas for that transformation is. LP1, this one, is equal to Km over Kf over C1. Km is our magnitude scaling factor, which is 50, because we need 50 ohm for our double terminated shunt input circuit. Kf we just calculated, we need to use the radians per second. as a unit, and C1 again, that's from the table here, which is 0.618. So you substitute the values here and you get now your LP1, which is then 1.843 microhenries. Now for the CS1, which is this, the second value is 1 over the Km times Kf times L2. Again, L2 is this 1.6180. You just substitute the values for everything here and you now get 281.5 picofarads. Now similar form for the LP2, again Km over Kf, but this time with C3, which is then this 2. We just substitute the values and you get now 569.3 nanohenries or 0.5693 microhenries. Now CS2, which is this one, the fourth element in the high pass filter, which is 1 over, actually similar to this CS1, 1 over Kf times the L4 again this coefficient 1.6180, and you get now 281.5 picofarad, again the same value as the CS1. The final one is LP3, again using this coefficient, again Km and Kf we already know, so you get now 1.842 microhenries. You see actually they are symmetric, so this value LP1 is the exact same as LP3. CS1 is equal to the CS2, and just the LP2 is different actually here. Okay, now we have now the required values, but for the RS and RL we need the normalized values, so these are normalized. So RS prime, actually there should be a prime here that is actually multiplied by the Km, which is then RS times Km, which is 50. Similar for RL, which is then also 50. So we have our 50 ohm here, 50 ohm in all those 5 values are shown here. Let's collect the values here. We just determined so the 5 values for the capacitor and inductors and also the resistor values of 50 ohms. What is our design circuit? That's shown here. Now the first one is our prototype low pass filter 5th order Butterworth response, and this is now the transformed variation of that high pass filter. It is scaled. This is a normalized, which is also called unscaled, and this is our high pass filter, which is scaled from the transformation from the low pass to the high pass configuration. Let's look at the simulation results for this circuit. This is the Bode plot, just the gain. And we see the pass band gain is 6.02 dB. Why is this true? Because if you look at the circuit, it has a gain of a half because the RS and RL are both equal to each other. So at very high frequencies, you get a gain of 0.5. The pass band frequency is 8 megahertz. That's actually shown here. So 8 megahertz, and it is lowered by 1 dB, which is as required because we need a maximum pass band ripple of 1 dB. Stop attenuation, looking from the flat line here going all the way at the 4 megahertz, we actually go down to minus 30.27 dB, which is a difference of 24.25, which is at least 20, so that means this is also true. The cutoff frequency is another information here, which is actually shown here at 6.989 megahertz, so you go actually down from this flat line by 3.01 dB, and that was what we also have calculated from the frequency scaling factor, so this is also verified. So again, this is circuit, again the RS and all the other scaled values. So we can say all the values are correct because the specifications we need to have here are met. Alright guys, this is our example number 4 about the Butterworth response LC ladder high pass filter design. We have discussed the calculation, also verified these in the SPICE simulations. If you have any questions, comments, please let me know in the comment section. I will try to answer them as soon as possible. See you next time in another video. Take care.